Next up, we are going to be looking at the universal gravitational potential energy. So we actually cannot use mgh for gravitational potential energy anymore because little g changes when you're getting big distances away from the center of a planet. In fact, all you got to do is go to the Mount Everest, and little g, the acceleration due to gravity, is like 9.7 something. So when little g is not constant, when you're using big distances away from the center of a planet, and you're changing that so radically that little g is not constant, you have to use universal gravitational potential energy. And the equation for universal gravitational potential energy, which we symbolize by UG, is equal to negative, notice that negative, GMM over R. Now, a couple things to notice. One is that this is negative, and also that it's not over R squared, it's just over R. This equation right here only works if you set UG equal to 0 at R equals infinity. So let's just briefly talk about this whole setup. Like, what UG equals 0 at R equals infinity? What the heck's that? And why is this negative? Well, you can set 0 anywhere you want. And normally, what we've been doing so far is we set the ground, let's say this is the ground here, we set that at 0, and then we lift an object up and it's got positive gravitational potential energy. Now what happens if we set this point up here equal to 0? And that means if I'm lower than that point, then this is going to have negative gravitational potential energy. So if I set right here equal to 0, my pen here has something gravitational potential energy less than 0. All that means is that I'd have to do positive work to get it up to 0. In other words, if I'm in a hole, I've set 0 up here, I've got to do positive work to get it to 0 potential energy. Remember, all potential energy functions are relative to where you call 0. So what we're going to do is we need to find a place that's common to every place in the universe. What place is it that's equally distant from the Earth, from the Sun, equally distant from the center of our galaxy, and even equally distant from the center of Andromeda galaxy or anything else we can come up with? There's only one place that's equidistant from all those things, and that is R equals infinity. We have got to find a spot right here, R equals infinity, that's the only place that's equally far away from everything in the universe. How far is it away from Earth? Infinitely far away. How far is it away from the Sun? Oh, it's infinitely far away. How far is it away from the Andromeda galaxy? It's infinitely far away. So we are setting our 0 way up here at infinity. Okay? So let's say that this is infinity, and I'm reaching really high up there. It must be really tall to reach infinity. No matter where you go that's less far away from your object than infinity, your gravitational potential energy is going to be negative. Why? If our object, our planet or our sun or whatever we're dealing with is down here, here's infinity, we're always lowering it towards that planet or sun or whatever we're dealing with. So all gravitational potential energies are going to be negative. 100% of them, except for what is the gravitational potential energy of a system of objects that are infinitely far away from each other? That is the only time that we can set that GPE equal to 0, when two objects are infinitely far away. So things to note here are that this thing is only true if we set UG equal to 0 at R equals infinity. It's always negative, and it depends not on R squared, but on the distance between the two planets or two massive objects. So we'll get a lot more practice understanding this when we do this, and let's go ahead and start now with figuring out the energy of a satellite. The equations we're about to derive will only work for systems of orbiting satellites. This does not work for an object out in space. It only works for a satellite that is in orbit around another object. So here's a question. Is the Earth a satellite in orbit? So can we use these equations we're about to derive for the Earth and some other object Is the Earth a satellite in orbit? The answer is yes. The Earth is a satellite of what? Of the sun. The Earth is orbiting around the sun. So yes, you can use this for the Earth-Sun system, but you couldn't use this for the Earth and some rocket that wasn't orbiting that just took off from the Earth and is going straight away from the Earth. That would not work. But the Earth-Sun system, you could use these equations that we're about to derive. What we have right here is a situation like so. We've got a mass, m. This could be our planet or a sun or anything like that. And it's being orbited by a smaller mass, little m. And that little mass is right there, moving at tangential speed of v at a distance r from the center of our big mass, which could be our planet. So this is a satellite of little mass m, planet of big mass, big M. And let's figure out how to express the energies of the system of two objects. Nothing new. E total for our system is going to be the kinetic energy of the system plus the gravitational potential energy of the system. Now, you can't have potential energy without two objects. A mass all by itself in the universe has no potential energy, but our system of masses has potential energy. When we stretch them farther apart, they will have increased gravitational potential energy. So let's go ahead and take a look at this now. We're going to assume that this central mass is not moving, so that we have our kinetic energy all comes from the motion of what? Our satellite. So 1/2 mv squared is the kinetic energy of our satellite. Again, this derivation only works for satellites in orbit. What is our gravitational potential energy? And this is for the system of the two masses. It is negative g big M little m over r. In order to use negative gmm over r for GPE, we have to assume that UG equals 0 where? When these two objects are infinitely far apart. So UG equals 0 when r equals infinity. You would not know this ahead of time, but we need to rewrite the kinetic energy term. And we're going to show how to do that right now. The force of gravity is also acting as the centripetal force. And notice we've done this before. This is nothing new here. Gmm over r squared, that's the force of gravity, will equal mv squared over r. And you may mention, well, why am I bringing this up now when we're dealing with energy? Why do I want this force in there? Well, I want you to notice what is something that 1/2 mv squared has in common with something down here. What do you see commonality there? Well, check out that. It looks a lot like this, except I've got to do a little bit of work to it to make it look exactly like that. So what I'm going to do to both sides, if I want to make this look exactly like that, make the centripetal net force look exactly like the kinetic energy, all I've got to do is multiply both sides. Let's do that right now. What do I got to multiply this by? Well, I've got to get this 1/2 in there, so I'm going to multiply by 1/2, and I do that right there, multiply that by 1/2. And then I've got to multiply this entire side by r, which cancels that r, and then it will also cancel one of these r's. So notice what I'm left with is 1/2 mv squared, which is what I was trying to find another equivalent expression for, is equal to this. So this is all based on, again, based on this, the setting the force of gravity equal to the centripetal net force. I can get this expression right here for the kinetic energy. This, however, right here, this half of it, is an expression of the kinetic energy of a satellite in orbit. Therefore, the kinetic energy of a satellite in orbit can be expressed by this. K equals G big M, the mass of the planet it's orbiting, little m, the mass of the satellite, over 2r. That is the kinetic energy of a satellite in orbit. It only works if it's a satellite in orbit. And then that is very important to realize that that is a positive number. Kinetic energy cannot be negative. It can never be negative.
Now we can finish deriving
the equation for the total energy of a satellite
system.
That means its gravitational potential energy and its kinetic energy all sum together. So we've already done it for the kinetic energy of it. For a satellite in orbit, and again, this only works for satellites in orbit, we have the energy total is equal to the kinetic energy plus the gravitational potential energy. This is what we just derived for kinetic energy. GMM over 2R, again, only works for a satellite of mass m orbiting a big old planet or sun of big M, and where R is the center-to-center distance between them. Notice this kinetic energy is positive. But we're going to add to that the gravitational potential energy of the system, which is this. We need a common denominator, so we just get it as we multiply top and bottom by 2 here. That gives us a common denominator. And when you add this positive value for the kinetic energy and this negative value for the gravitational potential energy, we get the total energy
for the system of a satellite in orbit,
which includes both kinetic and gravitational potential energy, is this. It's negative GMM over 2R. This only works if you set UG equal to 0 at R equals infinity. This only works when you do that. Now, what does this mean that it's negative? The total energy is negative. Well, let's understand what it means to have zero energy. If a satellite, and really it couldn't and still be a satellite, but if I had a satellite in orbit right here, let's go ahead and draw this right here. Here's my big mass out here, and here's my satellite just orbiting this big old mass right here. So this is little m, and this is big M, and the distance between the two is R. If I could take this away and get it all the way to R equals infinity, how much energy would that have if it was at R equals infinity with V final equals 0? How much energy would that have there? If I could get it infinitely far away with no speed, it would have 0 energy. So that means that our satellite in orbit has negative energy, which makes perfect sense. It is trapped in orbit below the R equals infinity. It's lower than R equals infinity. So it's got negative energy, meaning it's in a potential well. Its total kinetic energy and gravitational potential energy add to something less than 0. In other words, it cannot make it unless we give it a major push. It can't make it out to R equals infinity and end up at rest out there, so it has 0 energy, or for that matter, have any kinetic energy when it gets out there at all, because it is it's kind of like in a hole. It's trapped around this planet. So that means it doesn't have enough energy to get infinitely far away. We'd have to add energy to it. That's why this total energy is negative. This only works for satellites in orbit. It doesn't work for a satellite that's not in orbit. It doesn't work for any other masses anywhere else in the universe, but it is very convenient for a satellite in a circular orbit. If you have a situation where it is a elliptical orbit, though, you can use this. That would be negative G big M little m over 2A, where A is the semi-major axis. So anytime you see an R, you can pretty much substitute A, which is the average radius for an orbiting planet, even if it's an elliptical orbit. So we may need this if we're dealing with elliptical orbits.